Expressing solution concentration. We sometimes use qualitative descriptions, and these would include the terms dilute solution and concentrated solution. These are just relative to each other. A dilute solution is going to have less solute, and a concentrated solution is going to have more solute, but they don't really specify how much. And then there's a whole bunch of different quantitative measures. Here are some of them. We've got molarity, molality, mole fraction, mole percent, parts by mass, parts by volume. You can also have a mass volume percent. Why do we need so many of these? I don't know. Because we can't agree? No, it's actually a matter of convenience. So it really depends on what you are doing, which concentration you're going to use. In chemistry, we look a lot at chemical reactions. We're concerned with how this particle and this particle are reacting. We look at mole ratios. And so molarity is very useful because it gives us the moles in a measurable volume of the solution. So it's easy for us. Things like mass percent are useful in other fields where they're just trying to make the solution the same as the other person made it. They're not doing any stoichiometry. They maybe don't even remember what moles are. Mass percent or parts per million, parts per billion, these sorts of solutions are very easy to make. If you want a 10% solution and you want 100 milliliters of it, 10% is 10 parts out of 100 parts. So you weigh out 10 grams of your solute, you put it in something, you add water until you get to 100 grams, done. You don't really have to do any calculating. Whereas to make a 10 molar solution or a 0.1 molar solution, you'd have to know the molar mass, and you'd have to do some more calculating. And then you're also weighing out an odd number. So they're useful for different situations. The ones that are most important in chemistry would be molarity and perhaps percent by mass, but really molarity is the big one. But we are going to cover the rest of these. So molarity we've already talked about, so this will just be a brief review. Molarity is the amount of solute in moles divided by the volume of solution in liters, and it has to be liters. A disadvantage of molarity is that it is slightly temperature dependent, because if you take a solution and you heat it up, the volume of the solution will increase a little bit. And so then the volume's different, that makes the molarity different. So molarity will decrease at higher temperatures. It's not a big difference, but depending on your application, it may be significant. This is just a quick review of how you make a solution. So here we've got a volumetric flask that's a 1 liter flask, and we weigh out 1 mole of sodium chloride, which is 58.44 grams, if we want to make a 1 mole per liter solution. You put the solute in, you add water, you get it mixed up, and then you fill it up to the line. That's 1 liter. And then you need to cap it and invert it and make sure that it's thoroughly mixed. Any questions? Hopefully that's all reviewed. Molality, which I personally don't like, but people use it, and they have good reasons for using it. I just don't do anything where I need to use it. So molality, that's not a typo. That is an L, and it's intentional. I often get people on an exam, they're like, oh, well, I calculated the molarity. I thought that was a typo. Well, if you think it's a typo, please come and ask me, because molality is a thing. So molality is the amount of solute in moles, again, but instead of the volume of solution in liters, we're looking at the mass of the solvent in kilograms, right? Why would we want to do this? Because the mass of the solvent does not change with temperature. And so molality is independent of temperature. This is important in some areas where you're making a solution and then you're going to use it at an elevated temperature. And you want the You want to know what the molality is instead of the molarity, because the molarity is going to change on you. This is abbreviated with an italicized lowercase m. That's not confusing. We've got MOL for mole. We've got M for meter. We've got M in front of something as milli. And then we've got capital M is moles per liter. Now we throw in this italicized M.
Italicized? My handwriting is...
Right? Yeah. I'm sorry. I'm sorry, but I didn't do this. We just have to deal with it. And so if you've got a solution, say that's 0.10 m, you'd say that's 0.10 molal.
Meters?
Molal. Not molar, molal. It's in the course outline. I have to tell you about it. Okay, parts by mass and parts by volume. These are a lot more useful. So parts by mass, we're looking at the mass of solute to the mass of solution. So all of these fall into the same pattern. The mass of the solute divided by the mass of the whole solution multiplied by a factor. So percent by mass, percent means per 100. So percent by mass is the mass of the solute divided by the mass of the solution times 100. And this follows the same pattern that percent is a part divided by a whole times 100. So here solute is the part we're interested in. The mass of the solution is the whole thing times 100. So we can calculate percent by mass. We can also use percent by mass as a conversion factor. 14% by mass means 14 grams of solute per 100 grams of solution. There's also parts per million, parts per billion, even parts per trillion. The reason that we have these is if you're measuring, say, the amount of lead in your drinking water, it's going to be a very small amount. Maybe it's 1 part per billion. Well, if you express that as a percent, it ends up being this really tiny number that's hard to deal with. And so that's why we have these other units. Parts per million, ppm for parts per million, is the mass of solute divided by the mass of solution, times a million. Okay? Parts per million, you multiply by a million. Parts per 100%, you multiply by 100. Parts per billion, you multiply by a billion. Okay? We're not trying to make things complicated. So if you see 15 parts per billion, 15 ppb, that means 15 grams of solute per billion grams of solution. So the city of Fresno sends you a water report every year. You may not have seen it, maybe your parents get it. And it's going to list all these different things they test for, and some of the units in there are going to be parts per million and parts per billion. And so you can look at that and say, oh, well, what if I had 150 grams of water? How much lead is in my water? And you could do that calculation. Because most of you are not going to, but that's fine. You could. Parts by volume is the same pattern, but we're looking at the volume of solute divided by the volume of solution instead of the mass. Again, times the factor. You could have percent by volume, parts per million, parts per billion by volume. So if we see a 22% ethanol solution by volume, that means 22 milliliters of ethanol per 100 milliliters of solution. Whether you use mass or volume just depends on the particular solution. For ethanol, it's easier to use parts by volume because ethanol is a liquid. And liquids are easy to measure with volumetric glassware. It's easier to measure them that way than to weigh them on a balance. But with a solid, you can't do a volume. Any questions? Now we have some examples where we're going to use these ideas. So using parts by mass in calculations. What mass of sucrose in grams is contained in 355 milliliters, 12 ounces of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.0 grams per milliliter. So there's like an infinite variety of problems that could be asked incorporating all these units. So you can't just memorize, bless you. You can memorize, bless you, but you can't just memorize a pattern of, oh, I know how to do this, I know how to do this, I know how to do this. You need to understand how they work together and be able to figure it out. So how do you figure this one out? Well, you read through it. We already did that. Writing down the numbers that are given is a good first step if you're not sure what to do. So we've got 355 milliliters, and we've got 11.5% sucrose by mass. So we've got a solution here, right? That means there's a solute and a solvent, and we could have volumes or masses of both of them, so we probably need to identify 355 milliliters of what? Solution or sucrose? Solution. So it's 355 milliliters of the solution. Chemists get tired of writing the entire word, so we abbreviate it SOL''N. 11.5% sucrose. 11.5% means 11.5 per 100. And it says that's by mass. So this is, we'll put grams on the top and grams on the bottom. The nice thing about mass percent is you can use any mass unit that you want, as long as you use the same one in the numerator and the denominator. So it's going to be 11.5 grams of what? Of sucrose. 11.5 grams of C12H22O11 per 100 grams of what? Solution. Okay. It is just dimensional analysis. Exactly, and I did not pay him to say that. 1.04. I have no cash on me. I have children. 1.04 grams per milliliter is the density. Grams of what? Milliliters of what?
No, that's the
Grams of solution per milliliter of solution. So grams of solution per milliliter of solution. Okay, so we've got some things there. This looks like a conversion factor, right? That looks like a conversion factor.
It's all a conversion factor.
Is 35 milliliters of solution a conversion factor? No. Do we need this 12 ounces in there at all? No. That's just to sort of give us an idea. Oh, they're talking about a 12-ounce can of soda. It's 355 milliliters. So this is dimensional analysis. We're going to start with the 355 milliliters, and what do we want to end up with?
grams of sucrose.
Grams of sucrose. So we'll stick grams of sucrose over here, grams of C12H22O11. Yeah, I don't know why that seemed wrong, but it's not. Okay. So we're going to figure out how we can get from here to there, and these will probably need to be used. Well, if I'm starting with milliliters of solution. If I use this density, I could get to grams of solution. Right? So that's probably a good first step. Go to grams of solution. And then this relates grams of solution and grams of sucrose. Here I've got grams of solution, there I've got grams of sucrose. Oh, cool. It's going to be one really long arrow, but it's just one arrow. Any questions about how to get the path? That's really the hardest part. So now that we have the path, we can just do the problem, because the path is going to tell us what to do. So we start with the starting thing, 355 milliliters of solution. We have two arrows. We're going to have two factors. The first factor has grams of solution in the numerator, and it's going to have milliliters of solution in the denominator because we want those to cancel out. And the next factor is milliliters of solution to grams of solution to grams of sucrose. So this is going to be grams of sucrose, C12H22O11, and then grams of solution in the denominator. And grams of solution unit cancels out. Okay? Then I just go and look at what I had up here. This is grams of sucrose to grams of solution, so that's going to be used over here. I need to make sure I get the numbers with the correct unit. 100 was with grams of solution. So I put 100 here and 11.5 on the top. I don't have to worry about, was I supposed to multiply or divide by the percentage? The units are telling me what to do. It takes a lot of the thinking out of it. And then here, grams of solution, milliliters of solution, that comes from the density. 1.04 grams of solution. So the 1.04 is in the numerator. There's no number in the denominator. If that bothers you, it would be a 1. So then we just calculate 355 times 1.04 times 11.5 divided by 100. Yeah, 42.458, and we should have 3 sig figs. So 42.5 grams. 12-ounce can of soda, 42.5 grams of sugar. Yeah. Just want to point out this 100 here, 11.5 parts per 100 parts. That's from the percent. That's an exact number. The sig figs are in the numerator. There are 3 sig figs there. Any questions? Okay, mole fraction. Mole fraction has the symbol capital chi. So chi solute is the mole fraction of solute. This is like a percentage without the times 100. So it's the part divided by the whole in terms of moles. So the mole fraction is the amount of solute in moles divided by the total moles, solute, and solvent. So another way we can write that is like this. Chi solute is moles of solute divided by the sum moles of solute plus moles of solvent. If we want that as a percentage, the mole percent is just the mole fraction times 100%. Excuse me. Oh, this is a fun one. So a solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. Molarity, mole fraction, molality, mole percent, percent by mass. Fun?
No.
So fun.
And people wonder why there are more careers in chemistry.
But we need people that can do this. Okay. Let's start at the top, molarity. So doing a problem like this, first make sure you clearly understand, well, what is molarity? Moles of solute per liter of solution. So I'm looking for moles of solute, and here my solute is the C12H22O11, the sugar, divide by liters of solution. Liters of solution. Okay, so I need the moles of sucrose and I need the volume of solution in liters. Did they give me either? No, that wouldn't be any fun. How do I get moles of sucrose? Grams to moles. So I've got 50.4 grams of sucrose, C12H22 11. I need the molar mass, and then I can convert that. What's the molar mass of sucrose?
342.296.
Let's see. The answer is about 342 grams per mole.
Yeah, 342.3. What he said. So 342.3. Yesterday I calculated it, but today I'm tired. Okay, so 50.4 divided by 342.3. 0.147. One more. Oh, that was a brief one, but thank you for participating. Where was I? Up here. Okay, so how many sig figs should this have? 3. This has 3, that had 4. You usually want to make your molar mass at least the same number of sig figs as the other things, preferably more. This is not a final result. I'm going to use this in a calculation. So I want to indicate that it has 3 sig figs, but I don't want to round it off yet. So I'm going to add 2 more digits from my calculator to 4. And that's moles of sucrose. C12, H22, O11. Okay, so put that in here, 0.14724 moles per. They gave me the volume in milliliters. Is it 355,000 liters? 0.355 liters. So I think everybody's got that converting between milliliters and liters involves moving a decimal point 3 places. Some of you are still doing it in the wrong direction. So you could write the thing out or think about what you know. So 355 milliliters. Well, you know approximately the size of a 100 milliliter graduated cylinder, right? So that's like 3.5 of those. And you know how big a 2-liter bottle of soda is, right? So your choice is 0.355 liters or 355,000 liters. If you stop and think about it for like 10 seconds, you'll realize that it can't be 355,000. Okay. So 0.14724 divided by 0.355. This is a final answer, a molarity, and so this, I'm going to round it to 3 significant figures, 0.415. Units are moles per liter, or 0.415, capital M. Questions? Mole fraction. What does mole fraction mean? So some moles of the solute. Here it's C12, H22, O11. I'm tired of writing that also, but I'm going to do it anyway. Over the moles of solute plus the moles of solvent. So we've got the moles of C12, H22, O11, plus the moles of the solvent, which is water. So moles of H2O. That's the mole fraction. Well, we already know how many moles of sucrose we have. 0.14724. And that shows up again in the denominator. How many moles of water?
15.02. Are we doing one?
Well, not,
It's 0.332. I didn't see that.
so we've got 0.332 kilograms of water, and we need to convert that to moles. So 0.332 kilograms, 332 grams. So 332 grams, and the molar mass of water is 18.02 grams per mole.
18.423.
That sounds right. 18.424. That number should also have 3 sig figs, and I'm carrying 2 extras, moles of H2O. So I'm going to put that down here, 18.424 moles. And then we calculate this, being careful to not miscommunicate with the calculator. So 0.14724 divided by, and then open parentheses, 0.14724 plus 18.424, close the parentheses, equals, ooh, not enough room, put it up here, 0.00793. What's the unit on that? No unit. Moles divided by moles, it's unitless. Questions?
So your mole fraction does not end up in a fraction.
It's a ratio.
Well, it is a fraction, but we convert it into a decimal number. Yeah, I do occasionally get people who, you just paid too much attention to your math instructor. They'll take this and they'll add those two, and then they'll try to simplify it and get me a fraction like 2/3 or something. No, we're just going to use the calculator. Just give me a number. Molality.
Moles over kilograms.
Moles over kilograms. Yeah, moles of solute, C12H22O11, divided by kilograms of what? Solvent, H2O. Not the whole solution. Okay, so we have these numbers. Again with the moles, 0.14724 moles of sucrose per 0.332 kilograms of water. So 0.4395. I don't remember getting that number yesterday. Maybe I screwed it up. 0.4395. This should have 3 sig figs, right? So how do we write this? How do we round that? 0.440. So the 5 says we have to round the 9 up to a 10. So that rounds the 3 up to a 4, but we still need 3 significant figures, so we need to put a 0 there. And then this is moles per kilogram, or 0.440 m molal. Questions? What about the mole percent?
Is it the mole of the solute or the mole of this solution?
It's moles solute divided by so tedious.
So it's the same thing as the mole fraction?
But what makes it a percent?
The percent sign? Are you kidding me?
Times 100%. I'm not even kidding you.
Yes. Just a joke. What's the whole point of having a mole fraction then? take it away?
We're going to use mole fraction. Using mole fraction comes up in some of our calculations, and then we don't have to divide by 100%. So there are fractions with percentages too. It's just that you just divide by 100 and you get the fraction. So we actually didn't really have to write all that out. It is the mole fraction from above, 0.00793 times 100%. So 0.793%. Any questions? Percent by mass. So this is mass. We can choose what unit we use. Grams is good. So grams of solute
Over grams of solution.
divided by grams of solution
And solution is just water.
times 100%. The solution is not just
It's the
water.
water plus the
It's
sucrose.
the water plus the sucrose. So the mass of sucrose is 50.4 grams, divided by the mass of the entire solution. So it's the 50.4 grams of solute plus the 332 grams of water times 100%. A common mistake in doing a problem like this is you'll forget to add in the mass of the solute. I guarantee there will be a question on the 5th exam where I will try to trick you. I'll give you the mass of the solute and the mass of the solvent and ask you to find the percent by mass. And some of you will take the mass of the solute and divide by the mass of the solvent times 100 and come up with one of the multiple choice answers, and it will be wrong. You have to add the two together. So it's 50.4 divided by, open parentheses, 50.4 plus 332, close parentheses, times 100 equals. And this would also be 3 sig figs, 13.2%. No questions? Uh-huh.
Part B and D, is there a reason why you just didn't write moles as solution?
That's a good question. So for mole fraction and mole percent, in the denominator, why didn't I just write moles of solution? Well, how are we going to find the moles of solution?
Adding the moles of the solvent and solute.
The only way we can find it is by adding moles of solute to moles of solvent. That's the only way you can do it. So that's why I wrote it out that way. Look at the percent by mass and the mole percent. Are those the same number? We've got 0.793% by the moles and 13.2% by mass. It's really different.
Well, the mole fraction is not a percent. The mole percent is a percent. Right?
Well, but the mole percent is a percent, the 0.793.
The mole fraction is not. Oh, you're talking about the mole percent?
I'm talking about this one and that
Oh,
one.
I thought you were talking about the
No.
mole percent, mole fraction. I'm like, well, yeah, it's
No.
the same
Well,
number. It's just 1%.
No, D and E, different numbers.
Gotcha.
That's because sucrose has a high molar mass and water has a low molar mass. And so whether you're looking at it by mass or by moles, the percentages are going to be really different. Any questions?
Could you just say you're given the percent by mass and you're given this, or you're asked to find a mole percent? Could you just convert the mass into moles?
Yeah, that would be a fun problem. You're given a percent by mass and you have to find the mole percent. And
Did
so
I just give you an idea? I'm sorry if I did. Don't use it.
no, I actually just use the questions out of the test bank because it's easier. But there's very likely something like that in there. One more. So this is kind of like that. What's the molarity of a 10.5% by mass glucose solution? The density of the solution is 1.03 grams per milliliter. Well, again, good idea to just take the numbers that you're given and write them down. So 10.5% by mass. So that means 10.5 grams per 100 grams, right? It's 10.5 grams of glucose, C6H12O6, per 100 grams of the whole solution. And then we're also given a density, 1.03 grams per milliliter. That's the density of the solution. So it's the mass of the solution divided by the volume of the solution. And then they're asking for molarity. So molarity equals what? Moles per liter. So moles of glucose per liter of what? Solution. So those are the two things we have to find. Moles of sucrose, liters of solution, then we can plug them into the molarity equation. Glucose, yes. All those other ones were sucrose. And I fought the urge to say glucose, and I succeeded, and now I'm screwed. Okay, so how many moles of glucose are in the solution? 10.5 in 100 grams, 10.5 grams in 100 grams, right? How much solution are we talking about?
1.03 grams per milliliter.
Well, but that's not a quantity, that's a density.
But that's how you get the liquid quantity of your mixture.
Right. But do you see the problem here? This is a conversion factor. This is a conversion factor. What are we going to apply them to? We need a starting number. We need to just pick something. We need, because the percent, the density, the molarity, those are the same no matter how much of the solution you have. If you have a teaspoon or you have 5 gallons, right? Those quantities are all exactly the same. We need a starting point. So we just choose an amount so that we can do the calculation. This isn't the only way, but this is the way that makes sense to most students.
And we should start with grams of glucose, correct?
Well, we can start wherever we want, and people will have different ideas about where to start. I say let's pick something that's going to make our lives easier, right?
Like something, like what
So,
something.
well, how about if we just picked 100 grams of solution? Would that be easy? So if we picked 100 grams of solution, so 100 grams of solution would be 10.5 grams of sucrose blanking on numbers per 100 grams. We didn't really even need to do that calculation, but those cancel out. So if we choose 100 grams, then we have a starting point. We have 10.5 grams of glucose. Everybody okay with that? Why did I choose 100? Because it seemed like a good idea to me. You can choose anything you want. You could choose Avogadro's number of grams if you wanted to, but it's going to be a little messy. The numbers are going to be messy. You could choose 1 gram of glucose. You could choose anything you want. My point is you need to choose something to have a starting point, and then keep that for all the calculations. So I'm going to delete this dumb calculation that I did right here because I want more space. So if I have 100 grams of the solution, then I know I have 10.5 grams of glucose. I need moles.
156.
156? Thank you. So, M, 156.2. So we convert grams to moles using the molar mass. So 0.05. This should have 3 sig figs. And then keep 2 extra ones. So there's my moles. 0.058269 moles of glucose. Now I need to know the volume in liters of my solution. I picked 100 grams of solution. 100 grams of solution. How do I get the volume? Use the density. So I have grams of solution in the bottom and milliliters of solution on top. And it was 1.03 grams per 1 milliliter. That's the density. Grams of solution cancel out. And then I need this in liters. So milliliters on the bottom, liters on top. Milli means 10 to the minus 3. I put milli on the bottom and I put 10 to the minus 3 on the top. So 1 times 10 to the minus third, 1 milliliter. You could do that in your head as well, but there's just an example. So 100 divided by 0.03 times 1 EE minus 3. So the volume of that is 0.097087 liters.
I did something way different and simpler, but I got the same answer.
Okay, what'd you do?
I just took. I just did the 10.5 grams glucose over 100 grams solution times the density times the mole of that, and got that, and then multiplied that by that too.
That works too?
Oh, I get the same answer.
Yeah. So there are definitely different ways you can approach this. What he was saying is he took the density, the mass percent here, and converted the numerator from grams to moles, converted the denominator from grams to milliliters to liters, and then you've got moles per liter. Depending on how your brain works, that may or may not be simpler. I see a lot of people screwing up when they have to convert units on the numerator and the denominator, and so that's the main reason why I do it like this. But it's definitely not the only way. Any questions?